we're back in the physics classroom. We are rolling into rotational kinematics. They can't all be good jokes, kids. They can't all be good jokes, but that was a joke for sure. Happy Tuesday. Today, we're talking about circles and rolling, particularly tires and how they roll on the ground. So far, everything that we've done, we've said that rolling doesn't really, quote unquote, count. We've used rolling tires to negate friction with some of our stuff. But now we're actually going to discuss things that do roll and how they roll and some kinematics around that. So today, our intro to rolling is, do you know circles and how well do you know circles? So first question, let's talk about these three big questions that we have on the board. It's about circles. I have got up here some old tires. Why do I have old tires? Because they wanted to charge me to throw them out. And I said, no thanks, put them in the truck. I'll bring them to school. I'll find a use for them. Well, now we have a use for them. So I've got these tires, and they are round. They're circles. And so I'm going to ask you a question. I'm going to travel 5 kilometers in my truck with these tires. When I do that, I'm going to ask you, how many times is this tire going to rotate as I travel linearly across the road 5 kilometers? Let's assume we're going straight and there's no slipping or sliding. I'm just rolling forward 5 kilometers, 3.1 miles with these tires. That's the first question. And so in order to answer that question, I kind of have to understand something about circles. And that's not a perfect circle, but close enough. But if this is a circle, and this is my radius of the circle, tires rotate around that pivot point, around that axis of rotation. So as this thing rolls, if it does roll one rotation, it has traveled a distance that is equal to its circumference. And I hope that that's not earth-shattering to you. Maybe that's like an aha moment. I've never really thought of that before, but that's true, right? If it rolls one rotation, one complete circle around, that distance it's traveled linearly is one circumference. So we would say that this is 2 pi r distance, the radius. We might say it's pi times the diameter, distance, whatever we measure. But this is how I measure circumference, okay? And so if I wanted to travel 5 kilometers, I'd have to figure out what the circumference of my tire is, and then do a little algebra, some unit conversion to figure out how many rotations I made. Let's make a conversion factor. First, let's figure out what the circumference of this tire is. Hopefully, you've got some paper out and we can take some data. I've got my meter stick here, and it's a good thing we're doing kilometers because I'm only going to measure this thing in meters. Now, I want to think about where is this tire going to rotate around. It's going to rotate around the outside edge. I'm not trying to measure the interior radius, the interior diameter. I want the entire diameter of my tire because that's what's in contact with the road. All the way to the ground, all the way to the top. And what I'm looking at here is I see at the very edge where my tire sits, it's 75 centimeters or 0.75 meters. That's my diameter, my outside edge. So we'll say the diameter of the tire, 0.75 meters. Got it. If I wanted to find my circumference, I would do this times pi. So circumference is equal to 0.75 meters times pi. And I'll grab my calculator from behind the whiteboard. We can actually figure out my circumference here. 0.75 times pi. I get an answer of 2.35 meters per rotation. This is a conversion factor. I know that every time that tire rotates, it travels 2.35 meters. Let's go ahead and actually check that out. And we can check that out, right? We can go ahead, and I right now have on here, I've marked edge of my tire with this hook screw. And so I'm going to go ahead and start it right here. If I start it here, okay, we'll mark on the floor where I start this thing. We'll start it right at the hook screw. Bang, boom. There we go. Marked it out. Boop, on the ground. There it is. That's where I start. And now let's roll this thing all the way around until we get itself back to where it should be, over the hook screw right there. There's that distance right here. We can actually see, did we go 2.35 meters? Let's check. Here's where I started. I started at, there's 1 meter right there. Let's go ahead. flip it around. There's 2 meters right there. Flip it around. 2.3, it's pretty close. It's like 2.39, so it's pretty darn close, okay? And the reason it's close is because there's some give to the tire. That's how tires work. There's air inside them. This one has no air inside, I guess. I mean, it's not inflated, so it squishes a little bit. So there's some deformation, but we're pretty close to that number. 2.35, 2.38, we're right there. This is the distance traveled per rotation. So I'm asking you, how many rotations does a tire make to travel 5 kilometers, 5,000 meters? How many rotations will it take? Well, if I'm going 5,000 meters, and I know it's 2.35 meters per rotation, I should be dividing 5,000 meters by 2.35 meters per rotation. And I end up with my answer. It's got to be somewhere in the thousands, right? Like, holy smokes. 5,000 divided by 2.35 gives me, 2,127.7 rotations. There it is. How many rotations will a tire make? That's a lot. That's a lot of rotations, 2,000 rotations to simply go a 5K, 3.1 miles. That's pretty cool. Question 1 answered. We understand circles a little bit. Circumference is a measurement around the edge of a circle, like our tire. But when that object rolls across the floor without slipping, like we just saw, as the rolling motion propels it forward, we can use that measurement also to tell us how far we've moved linearly. There's clearly some kind of relationship between rolling and moving in a straight line or moving down the road like we see with our tires. Question 2 makes this a little more complicated, okay? If it takes me 10 minutes to drive 5 kilometers, how fast am I driving? It's not really related to circles. I can actually just do this by simply taking my distance and dividing it by my time. I could do kilometers per minute. I'd rather do like, meters per second or meters per minute. We're more familiar with those things, so let's do that. Let's go ahead. I'm going to keep that number there. We'll need that in a second. But for now, happy Tuesday! But for now, let's just do 5 kilometers. Convert it into meters, 5,000 meters. And let's take 10 minutes, and we'll convert that over into seconds. And 10 minutes, 60 times 10, 600, right? 60 minutes, 60 seconds in a minute times 10, I get 600 seconds. So to find my speed, or my average speed of this object, to be distance over time, 5,000 meters over 600 seconds, I'm left with, what is that? Average velocity is 8.33 repeating meters per second. And that's pretty fast, right? I'm going 8 meters per second. So if one revolution was 3.5 rotations, I'm going 8 meters per second, okay? One revolution was 2.3, right? 2.35. So I'm going 8 meters per second here linearly across the floor. That's wonderful. I can conceptualize 8.33. I've seen 8.33 in the classroom moving linearly. We've launched objects across the room at 8.33. That's not a crazy speed at all. The last question, though, asks us to think about what is the rate of rotation of my tire. So when I think of rate is typically something per time, right? It's either distance over time, but in this case, it's rotations, a rate of rotation. So I'm thinking rotations per time. So how many rotations did I make over this time interval? Well, the time interval, or the number of rotations I made, was 2127 rotations. And I made those rotations in 600 seconds. So how many rotations per second was that? It ends up being 3.5. 3.5 rotations per second. This is my rate of rotation. Okay, so I've got a couple different things here, right? I've got distance. I've got distance over here. I've got my angular or rotational distance, which is number of rotations. I've got my angular or rotational speed over here, or rate, which is rotations per second. These are very similar to distance, meters, very similar to velocity, which is meters per second. So it's almost like we're replacing, when I'm translating between my linear motion and my rotational motion, I'm simply translating between meters and meters per second over to rotations and rotations per second. And if we brainstorm some various measurements of rotation, we know degrees. There's 360 degrees in one rotation, so I might even call this degrees per second. If you're in math class right now thinking about the unit circle, you might say radians is a measurement of angle, so we have radians and radians per second. And we want to give these values variables. So we have this thing here. We're going to give this thing a name. This type of angular or rotational distance has a name. It's called angular displacement. And it is equivalent to x. It's equivalent to distance or displacement in the linear motion. It is a synonym to that. If I rotate a certain number of rotations or degrees or radians, it's very similar to moving a certain number of meters across the floor. Its variable is theta. For degrees, how many degrees, how many radians? Theta tells me how many revolutions or rotations an object makes as it moves. This over here, if that was angular displacement, guess what we call this? We call this angular speed or velocity. Angular speed is revolutions or distance in the angular or circular direction over time. This is called angular speed, and its variable is a lowercase omega. So it's like a curly W. If you're a Washington Nationals fan, it's like a Washington Nationals logo. It's a curly W, kind of like this. Okay, a lowercase omega. Some people call it a W. These are your two variables we're discussing today. These are the intro variables. These are the synonyms over to displacement and velocity in the linear direction. Again, all unit long, we are looking for our comparison variables. What do we know from first semester and basic kinematics and forces, and how are they related to these variables here in second semester and in rotational motion? Okay? If you got questions or if I screwed something up, drop in the comments, send me an email, or ask me in class. Until next time, see ya!